schools, what we really want to be doing is adopting this two-stage approach where we have an element of design. So we create a design for our program, and then we go and take that design and turn it into code on our computer. And we call that second step coding, and we call this process overall programming. So this was the kind of the model that we set out, Barefoot sets out, and is followed generally by other organisations in this idea of what programming is. And we used this model last week to go through two activities around some concepts, some of the basic building block concepts that make up most programs. So let's look at where that kind of comes in the Scottish curriculum. So we have our technologies strand, and we've got the experiences and outcomes document created on here. And within computing science, we've got these 2 points around understanding and analysing the technology, the computing technology, and then designing and building and testing as well. And throughout these, you can see reference to the kind of concepts which we've covered, or covered partly last week and partly this week, around things like understanding sequences of instructions in the early level, then moving on to understanding visual programming language, of which Scratch is one, and then sort of the moving on further, generally understanding the kind of computing concepts, core programming language concepts, which are, as it's called here. And if you look at the additional kind of documentation of from the benchmarks that kind of describes this in a bit more detail, but if you go through those and summarize it and boil it down and distill it down rather, and what drops out the bottom are these three building block concepts that all programs are made from. And there's only, we've done sort of reviews of programming coding curricula from around the world, and wherever they're based, they might use different language, it might be structured and organized differently, but if you go through them, they all boil down to these three concepts, because these are the three concepts which programs are built upon. They're like the Lego bricks for building everything else, and they are sequence, repetition, and selection. And what we did last week, we started going through each of these, doing a activity where we read some code, because I talked about the importance of not only developing pupils' ability to write code, but also to read code as well. We should view the development of pupils' programming sort of language acquisition, and just like any other language where you're developing the ability to read and write it at the same time. So we started with the first two last week, which was sequence and selection. And this week, we're going to finish off by looking at, we did sequence and repetition last week. We're going to look at selection this week. And I'm glad we've got a bit more time to spend on selection this week, because it is one of the more complex concepts. It's a very powerful one. It opens up the possibility for programs to respond differently to users doing different things. And it just requires, as a result, a little bit more unpicking. So I'll just fly through these slides to get to where we were, and also give a quick commentary. So these were the examples of the kind of code matching activities to develop your code reading skills, matching first of all the sequence one, and then you went and had a go at creating a sequence of code in Scratch, and that was the algorithm that we produced first. So following that model of creating a design first of all, and then going and programming it. And then we looked at repetition, and again we had our code reading activity, and I can't remember the name of the person, apologies, that did this one, but they spotted straight away that we had different types of repetition command in our Scratch code at the bottom here. The two types that we had were the forever loop and then the repeat fixed number of times loop, and they were able to use that information to match up with the top, the different code outputs. And we talked also about how algorithms are made for you, and you can choose however you want to represent your algorithm. So when we came on to creating a algorithm for our own dancing camel. We actually use this idea of having it written down, but we talked about how you could do it as a drawing, or you could get pupils to even act it out as their algorithm. It really doesn't matter what form that algorithm takes. So then we finished off last week by having a go at creating your own camels come dancing animations using the repetition commands, which we'd talked about a little bit. And that was where we got up to. So we'll pick things up here at selection, the final of the three concepts. And this is, as I say, quite a powerful one because it means that a computer can execute different instructions whether or not a condition is met. So that seems a little bit abstract perhaps. So let's put a simple example up from the everyday world around us. So this is what a selection command looks like in Scratch. It's the if then else command. It's in the orange blocks section, the control blocks. And there are basically 3 bits to it that we have to add other commands to. So the first part is at the top here. There is a hexagon section to the, an irregular hexagon section to the block. And we have to build a condition there. So in the everyday example that I've used here, the condition is I'm trying to be healthy. So we put that condition there. And then as we talked about last week, Scratch is quite an easy language to read. So if we read it now, it says, well, if I'm trying to be healthy, there's our condition, then if that condition is met, it's true, i.e. I am trying to be healthy, then any commands we place in the top part of that block will be run. Okay, so here it says I'll have a salad. So if I'm trying to be healthy, then I'll have a salad. Now, if we get to this command and this condition is not met, and we call that being false in computing science language, then the commands in the bottom part of the block will run. So this can be sort of viewed as a kind of a branch in our flow of control of our program, in that when the program gets to this block, it will make a judgment as to whether or not that condition has been met. And if it has, it will do the commands in the top portion. And if it hasn't, it will do the commands in the bottom portion. So here, as I said, I've used an everyday example to try and sort of simplify this. But in our program, it might be things like whether if the condition of lives equals 0, then it might say game over. But if lives are not equal 0, it means you can carry on playing. That's an example sort of moving us into the world of how this is used in computer games, for example. So let's do our first activity this afternoon, a code reading activity. Now this is slightly different to the previous activities, the previous code reading activities we did, because with those we looked at the code and then we matched it forward to the output of the program. Here what we're doing is we're looking at the code and we're matching it back to the algorithm which was written, which the code has been created from. So I'll go quiet and I will let you have a read of the 3 bits or snippets of code, A, B, and C. And I'd like you to have a go at matching them up to the relevant algorithms 1, 2, or 3, which were written that led to that bit of code being generated. So I should imagine we were quite speedy last week, so I should imagine we will be quite speedy this week. I'll go quiet for a minute or so, give you a chance to have a go, and just pop your answers in the chat however you think they match up. What's the general consensus, Louise? Can you match any of them up for me? 2A, yeah, okay. Would you mind? Yeah, would you mind picking on someone, please?
Yep. Yep.
Hi, well, thank you. I was just wondering if you wouldn't mind just talking through your thought process on how you went about matching these up.
So the first one, when I was looking at the pictures, obviously I'd read the algorithms, but actually the A is the one that jumped out because the broadcast end game in that different coloured yellow just kind of stuck out really very obvious to me. So that one was kind of jumped out at me, and the only, obviously algorithm 2's got end games, the only one that says that, so I knew those two went together. And again, then the other one for B, the purple block at the bottom, you ran out of time, obviously means there's a time element to it, so there's only one that's got that. So I suppose it was actually, as opposed to having to read through the entire code, it was scanning it, skimming and scanning it and picking out a specific, important piece of information that's specific to that algorithm that gave it away.
Yep, fab. And that's the kind of, that's a result of this kind of thing. It is, yeah, totally breaking it down. And it's a result of the Scratch language being closely aligned with with our algorithm language. As I keep saying, it's fairly easy to read the Scratch language, and it often is quite close to our algorithm as well. So that's super. Thank you for that. And so just to spend a little bit more time on these, hopefully you can all see that for each one of these, we've got these selection blocks. They might look slightly different. We've got the if-then block here, and here it's actually a repeat until, or just an if-then without an else. But for each one of these, we've got these conditions, as I mentioned on the slide before. So here the condition is just looking to see if lives equals 0. The one you were mentioning then about running out of time is if time equals 0. And one we're going to come on to is whether or not the answer equals the correct answer. So we're just checking whether or not a response is correct. So a key thing when working with selection blocks is building this condition that we're going to pop in the top there. So we're going to have a go at this now, and we're going to have a go at creating our own Camel's Conundrum quiz. So it's a times table quiz. So this time I'm going to give you the algorithm, and I'd like you to then turn that algorithm into code. So the algorithm is on the screen there, and I will leave that up. We're going to write a simple bit of code that poses the question, what is 7 times 8? And then it allows the player to respond. If they get the answer correct, we're going to say well done, and if their player's response is incorrect, we're going to tell them that they're incorrect, and we're going to tell them the correct answer. So look, I'm not going to get people to sign in this week to the Barefoot website. I'm going to drop this link into the chat there, and if I just get you all to follow that, then you should be able to see a screen that looks like this. If you can all see my screen, it will take you to Camel's Conundrum quiz starter code. And then if you click see inside, you will get to this screen here. So I'm just going to talk you around briefly what you've got here and the way we are scaffolding this for you. And then I'll go quiet and give you sort of a few minutes, 3 or 4 minutes to have a go at this one. So what we've done here is something called a Parsons problem. A Parsons problem is when you provide all of the bits of code that a pupil requires to complete a problem, but you don't show how they fit together. But you do have all of the code here required to complete the problem of getting it to ask the question, what is 7/8, and then respond. So just to kind of go through the different blocks that we've got here, we've got the if, then, else selection block. I'll just zoom in a bit so hopefully you can see it a bit better, which is this one here. So this is our main block for our program that we're going to create. You can see this was the irregular hexagon at the top here that I mentioned, where we're going to have to build our condition. The next block that we have, which is of significance, is this ask block. So when you run this, and I mentioned last week, you can run blocks in Scratch just by clicking on them. You'll see that it asks whatever is written in this field here, and then when the player enters, whatever they enter is then stored in this answer variable. Okay, so you can see there, I'm clicking on it, it shows me what is currently in there. So the little answer variable can be thought of as a bit like a mini whiteboard that pupils might use in the lesson, where they just store information on it. So we can use that then in our program. It might be that we could use it with this little operator block here to see whether or not the answer equals the answer we are expecting for what is 7 times 8. And then I think these are, you would have seen these blocks last week, these commands last week. If you joined, if you haven't, they're fairly straightforward. They simply say from the sprite whatever is entered in here. So I'm going to go quiet at that point, and I'm going to let you have a go. As Louise mentioned before, important with decomposition. It's a very powerful approach. Decompose this algorithm. I'll leave it up and tackle it a bit at a time. So first of all, first part is to just pose the question, what is 7 times 8? Then think about the next part. So how are you going to build that condition to test whether or not they are correct, and say well done if they are, and incorrect, and this is the correct answer if they are not. So what time are we on? 26 minutes past 4. I am going to go quiet for 4 minutes. Might not be able to stay quiet for 4 minutes, 3 minutes, until just before past. I'll let you have a go. Stick your hand up if you've got any questions, or jump onto the microphone, and we'll check in shortly on how you're getting on. Okay, give me another couple of minutes.
I put 56 in the second one.
Yeah,
and I
great.
wasn't quite sure if that's the right thing to do.
Yeah, is that what you've got up to do?
And yeah, then I've put, say, you know, if that is 56, then say well done for 2 seconds, else say wrong for 2 seconds.
Okay, you are very nearly there. So is that what you've got? Have I accurately? Right, okay. So the only thing you haven't done, that's absolutely spot on. All you need to do then is drop this into there, because what you've got so far is spot on. You did an extra hello here, but that is no problem at all. I was anticipating that would just go down in here, but you've done a nice polite Quizmaster. I like it. Then you've asked what the question is. Now, when it asks that, and I'll just run it from there, hello, and then it will ask, I'm going to then respond with my answer. So I might get it wrong and say 40. That response is then automatically stored in this little block, this variable, and I can show what's in it by clicking on it. There it shows as 40. What you correctly realized is we then need to check whether or not their answer equals 56. But at the moment, we're just checking if nothing equals 56. If we take that answer variable and drop it in there, it will now check whether or not their answer equals 56. And then you got it spot on. If it's correct, run the top bit. If it's incorrect, run the bottom bit. So if I run that now, hello, what's 7 times 8? If I get it wrong and put 60, it will say wrong. If I run it again, fingers crossed, and get it right, 56, well done. So, I mean, you are 99.9% there.
Yeah.
And I hope that's clarified the last bit for you there.
Yeah, yeah. And I knew there was something missing there. I just didn't know.
Yep. Well, there we go. That was it. So yeah. So thank you very much for coming on and sharing that. I'll wrap things up then and say thanks to everyone for joining, and say not next week afterwards. We're going to do the final session, which is going to be focusing on the pedagogy. So we spent a lot of time over the last 3 weeks looking at the kind of core concepts of computational thinking and then programming, and within that our sort of sequence, repetition, and today's selection. Next session we'll look at the emerging research-backed approaches to teaching all this kind of stuff. It's really interesting this to be part of a subject where the kind of pedagogy best practice is still emerging. The Raspberry Pi research group linked down at Cambridge University was officially, I mean, it's been running for a while, officially launched a couple of months back now, and they're doing a lot of research around this. And we're going to look at 3 or 4 pedagogical approaches which you can take and use with your learners. So we're going to look at something called PRIM that you might have heard of, which is a methodical approach that encompasses both code reading and code writing and kind of bridges the gap with some remixing of code. We're going to look at also something called use, modify, create, which is a similar kind of structure, talk about Parsons problems. So it's, yeah, we're going to sort of just share a number of tools with you of how actually you structure this stuff to best enhance pupils' learning in the subject. And I think it's a really interesting area because it's emerging all the time. It's developing all the time. I've tried to showcase a bit of it in this week's and previous weeks with providing examples of code or Parsons problems, but we're really going to dive into it in a bit more detail. So that's what's coming up, not next week, but the week afterwards.